Welcome to this explainer. Look, for all you incredibly focused scholars out there gearing up for your Cambridge exams, we are tackling a seriously high-stakes topic today. We're going to decode exactly how to secure those top-tier mark bands in AS and A-level Mathematics 9709. Specifically, we're zooming right in on Section 4.1, Forces and Equilibrium. We're going to completely demystify the dark art of resolving forces and finding resultants. If you've ever stared down a complex mechanics problem and just felt completely lost, or maybe you feel like you're doing all the math perfectly, but you're still somehow bleeding points on the actual exam, well, you are in exactly the right place.
Okay, let's dive into this. Check out this quote directly from a senior Cambridge examiner. They state it perfectly plainly. Students lose marks by not showing working. Even if your final answer is wrong, method marks can save you. That right there is exactly why this explainer is going to act as your ultimate insider's guide. We aren't just going to sit here and talk about the math in a vacuum. We're actually going to explore exactly how examiners award points on their marking grids. The goal here is to help you construct an absolute safety net of method marks. That way, even if you make some tiny, silly calculator error at the very end of a long problem, you're still walking away with the lion's share of the credit.
So here is our incredibly structured roadmap for today. We'll kick things off with core principles, move right into a 5-step resolution sequence, dissect those crucial method marks, review some critical examiner warnings, and then wrap the whole thing up with your final exam strategy. Let's get moving.
We're looking at mastering core equilibrium principles.
Now, before we even think about touching a calculator, we really need to look at how top-performing students approach this math totally differently than those who struggle. This comparison brilliantly illustrates the divide. On one side, we have what's called superficial breadth. This is basically when a student just memorizes basic formulas, force equals mass times acceleration, or blindly throwing sine and cosine at a triangle without any real context. On the exact opposite side, we have analytical depth. This is all about logical, highly structured reasoning. And here's the thing you need to know. The Cambridge Assessment Framework explicitly prioritizes this depth. They absolutely do not want you to just skim the surface of the syllabus. They want you to logically deduce why a force is acting in a certain direction, not just plug numbers into a memorized equation and hope for the best.
To actually achieve that required depth, Cambridge targets 3 specific cognitive domains, or assessment objectives. First up is AO1, knowledge and understanding. Basically, do you actually know the core principles of equilibrium? Second is AO2, application. Can you take those principles and apply them to the specific diagram in front of you? And third, AO3, analysis. This is the big one, guys. Can you break down a really complex system of intersecting forces? You absolutely need conceptual mastery across all 3 of these domains if you want to hit those top A-star mark bands.
Because really, here is the ultimate goal. Your knowledge has to be perfectly transferable to completely unfamiliar contexts. Cambridge is somewhat famous for throwing weird, highly specific, and slightly terrifying scenarios at you. I mean, you might spend all month practicing with little blocks on inclined planes, but on exam day, suddenly you're looking at a ladder resting on a rough wall with a pulley attached to a moving vehicle. But listen, the foundational physics hasn't changed at all. It's like a giant puzzle. If you have true analytical depth, you can seamlessly transfer your skills to absolutely any strange new exam question they decide to throw your way.
Section 2. Let's get into the mechanics of it with the 5-step resolution sequence.
Now, what's really interesting about this framework is that it provides an exact, standardized sequence for resolving forces. You literally never have to sit there staring at the page guessing how to start. Step 1, identify your key elements. So find your friction, your tension, your weight. Step 2, apply your principles, like, recognizing that a resultant force is exactly 0 when a system is in equilibrium. Step 3, execute your analysis, usually breaking it down horizontally and vertically. Step 4, verify if your answer actually makes physical sense. And Step 5, present your format clearly, using the correct notation and the right number of significant figures. Following this exact sequence essentially guarantees a structured, high-scoring answer.
To put that into an even punchier, more tactical sequence for when you're sweating it out on exam day, just remember this: deconstruct, extract, select, execute. First, deconstruct that super dense word problem. Next, extract all the numerical data. Pull out the masses, grab the angles. Then, select your analytical framework. Ask yourself, are we resolving perpendicular to an inclined plane here? And finally, execute your equations with crystal clear algebraic notation so the examiner can follow your exact train of thought without guessing.
Moving right along to Section 3, securing essential method marks. So securing these method marks is quite literally the difference between missing your target grade and achieving an A-star. Why? Because marks are awarded for your specific logical process, not just getting the right magical number at the end. Take a look at this table. At the most basic descriptive level, you're really just extracting data, like seeing a 5-kilogram mass in the text and writing down 50 newtons. Simple enough, right? But to reach the analytical level, you have to interpret relationships. You need to show exactly how normal reaction relates to the friction coefficient, for example. And then up at the highest evaluative level, you are actually justifying why a certain mathematical model is even appropriate in the first place. This means your data interpretation skills really need to be incredibly robust. When you're examining the relationships between different resultants, you have to extract accurately, interpret the complex force vectors at play, and draw really clear evidence-based mathematical conclusions. For instance, if an object is on the verge of sliding, your mathematical evidence has to clearly demonstrate that maximum static friction has actually been reached. You can't just state it, you have to prove it. Okay, on to section 4. This is absolutely crucial. Critical examiner warnings. We've spent a lot of time looking through the principal examiner reports, and it really begs the question, why do smart students, who totally understand the math, still lose easy marks on these specific traps? I'll tell you a secret. It is rarely because they don't know what a force is. It is almost always because of easily fixable formatting and presentation pitfalls. Let's actually look at the data. Here is a visual breakdown of the top 3 fatal errors directly reported by principal examiners. Number 1, forgetting proper format. This means skipping steps in your algebra because you did it in your head, or failing to explicitly state the direction of a resultant force. Number 2, failing to check your presentation. Look, examiners literally cannot award you method marks if they cannot read your handwriting or follow your chaotic all over the page working out. You have to keep your lines of equations linear and logical. And number 3, answers lacking specific context. You absolutely must anchor your final numbers to the physical reality of the question given. A number floating in space means nothing.
There are also these sneaky quality evaluation traps you need to dodge. If a Cambridge command word specifically asks you to evaluate, true evaluation requires identifying limitations and assumptions. Ask yourself, did you assume the pulley was perfectly smooth? Did you assume the string was completely inextensible? If you ignore the underlying assumptions made by the mathematical model or overlook how those assumptions actually affect your final conclusion, the quality of your evidence plummets on their marking grid. So always state your physical assumptions if the question asks for an evaluation.
Finally, let's head into section 5, your final exam strategy. Let's pull this whole thing together. Here is a powerful, totally actionable memory hack, straight from the source material. When you are under intense exam pressure, your working memory shrinks. It just happens to everyone. So, to easily retain all this complex equilibrium terminology and those procedural steps, create a mnemonic using the first letters of key terms. Think back to our procedural framework from earlier. Identify, apply, execute, verify, present. IAEVP. Come up with a silly, memorable phrase for that. Something like, intelligent aardvarks eat very promptly. Honestly, whatever it takes. Use these memory hacks so that your brain can free up its power to focus on the genuinely hard math rather than panicking about what step comes next. I want to leave you with this final provocative thought today. Have you actually mastered that 5-step sequence well enough to secure every single method mark, even when the final answer completely eludes you? Because remember, exam success isn't just about being a flawless human calculator, it is entirely about communicating your logical process so clearly that the examiner literally has no choice but to award you those points. Now, if you want to optimize your revision feed and make sure you never miss a strategy session, you need to subscribe to AC Exams at @ACExams, hit that notification bell, and drop a comment below letting us know exactly which Cambridge level, IGCSE, O-level, AS, or A-level, you are preparing to conquer next. Keep practicing, stay incredibly focused, and I'll catch you in the next explainer.